Okay, so we're looking at writing electron configurations. These are the same rules from writing the orbital notations. So we're following Aufbau's principle that says lowest energy level first. So we would fill 1s, 2s, 2p, 3s, 3p, 4s, and then come back and pick up the 3d. So this is where you have the first change in the configuration, so just be aware of that. Hund's rule, electrons fill one orbital at a time before they pair up, and then Pauli exclusion principle, two orbitals, two electrons in an orbital with opposite spin. So if we look at beryllium, for example, beryllium is number 4 on the periodic table, so it has 4 protons. So a neutral atom would have 4 electrons. We're going to fill the 1s first. S has 1 orbital, so we draw 1 line. Each orbital can hold 2 electrons as long as they have opposite spins. Then we would fill 2s. S again has 1 orbital, which can hold 2 electrons. If we were to look at nitrogen, nitrogen is number 7 on the periodic table, so 7 protons, 7 electrons for a neutral atom. We're going to fill 1s first, 2 electrons, 2s, s has 1 orbital, it can hold 2 electrons. Then we come to the 2p, which has 3 orbitals, so we would draw 3 lines. And then Hund's rule says 1 on each line before we pair up. We're at 4 electrons, so 5, 6, 7. Notice they're all going the same direction because that is the lowest energy. All right, there's a shorter way of doing this, which is called electron configuration. So this is called orbital notation. Electron configuration is the shorthand to orbital notation. And that's where we use exponents to show how many electrons are in that energy level and sublevel. So we would say 1s, and then there's 2 electrons, so 1s2, 2s, there's 2 electrons, 2. For nitrogen, we would say 1s2, 2s2, and then 2p, we have 1, 2, 3 electrons. So we're shortening it just a little bit. So what you have to remember is that s's have 1 orbital, so they can hold 2 electrons. So the exponent for the s's should always be 1 or 2. The p sublevel has 3 orbitals, so it can hold a maximum of 6 electrons. So the exponent for any of the p's would be 1 through 6. For D has 5 orbitals, so that can hold 10 electrons. So again, the exponent for any of the D should be 1 through 10. Now we won't ever write an F orbital at this level. If you take AP or DP chemistry or any chemistry in college, you'll get into the F, but we're going to stop at the D sublevel. All right, so let's look at some examples. Again, electron configuration is the shorthand for orbital notation. So if we look at, say, aluminum on the periodic table is number 13, so it would have 13 electrons. Aufbau's principle says we would start with 1s. S has 1 orbital and it can hold 2 electrons. Then we would go to 2s. S can have 1 orbital, it can hold 2 electrons, so we say 1s2. And then we have 2p. Now I'm at 4 electrons right now, and I'm trying to get to 13. So I'm going to go ahead and fill the 2p with 6 electrons. Remember, p can have up to 6. So now we're at 10 electrons. We're going to keep going. 3s. S can hold 2. That puts us at 12 electrons. So we have one more electron. So we need to go to one more, 3p, and then that's going to be our extra electron there. So the electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. Notice that I'm not saying 1s squared. We're not squaring anything, we're counting. So it's 1s2, 2s2, and so on. Let's look at doing iron. Iron is number 26, so it has 26 protons, so neutral would have 26 electrons. We start with 1s, which is our lowest energy, and it can hold 2 electrons. Then we have 2s, 2 electrons. That's 4. 2p, p can hold up to 6 electrons, so we're going to go ahead and put 6 in there. That's 10 electrons, 2 plus 2 plus 6. We're trying to make 26, so we're going to keep going. 3s2 gives us 12 electrons. Since we're at 12 and I'm trying to get to 26, the 3p is also going to be full, so I can say 3p6. And then this is where you have to be careful. After 3p comes 4s, and so that's 20 electrons. I have 6 more. After 4s is 3d. Now d can hold up to 10 electrons. I'm at 20, trying to get to 26, so I'm going to put those 6 electrons in the 3d. So again, you have to know Aufbau's principle, you have to know those orders, and then you have to know how many electrons can fit in there. The exponents are your electrons, so you can add the exponents together to figure out how many electrons you have. Now, it can get a little cumbersome trying to remember the order, trying to keep track of how many electrons you've done, so there is a shortcut. The periodic table happens to be arranged according to Aufbau's principle. So groups 1 and 2 are known as the S block. Notice that helium is a part of the S block, and that's because row 1 or period 1 only has 2 elements in it. So you can pretend that helium is over here to fill out those 2 or that group. And then groups 13 through 18 are your P block. Groups 3 through 12 make the D block. And then the 2 rows at the bottom make the F block. But again, we won't be coming down here or going through here at all. In fact, you have to be able to write electron configuration for any element up to number 56, which is barium. So we won't be going into the F block, but you need to know that it exists. So if we were to pick an element, actually before we do that, the row number, which is also called a period, tells you the energy level. So like we did aluminum, aluminum is in row 3, so I knew I had to go to the 3rd energy level. It's also in the P block, so I knew I had to make it to 3P. It's the first element in the P block in row 3, so I knew that it ended in 3P1. Iron is in row 4, so I knew I had to make it to the 4th energy level. It's in the D block, so I knew it would end in D. And if you count 1, 2, 3, 4, 5, 6, it's the 6th element in the D block. So that's how I knew it ended in D6. Now the D block has kind of been pushed down into the periodic table. So the D block is always 1 less than the row it's in. So this is 3D, not 4D. So the row number is good for the S and the P block, but the D block is 1 less. All right, let's look at an example. So let's take gallium for example. Gallium is number 31, so it has 31 protons, 31 electrons for a neutral atom. If we start at the top of the periodic table, and we're going to read from top to bottom, left to right, just like you're reading a book, you're on the first row, so that's 1, in the S block, so 1s, and there's 2 elements, hydrogen and helium, so 1s2. Then we go to the second row, so we would say 2, the S block, S, 2 elements, lithium and beryllium, so 2s2. Keep going straight across, you're on the second row still, but this time you're in the P block. 1, 2, 3, 4, 5, 6 elements are in there. And so we would say 2p6, and that gets us to neon. So we know that we're at 10 electrons so far because we've counted 10 elements. We go to the third row, and we would say 3s, there's 2 elements, 2. Go straight across, 3p, 1, 2, 3, 4, 5, 6, so 3p6. Now we're on the fourth row, so we say 4s, there's 2 elements, 1, 2. Now we're in the D block, so we're 1 less than the row we're in. So this would be 3d, and then count your elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're back to the P block, so we're back to the row number 4. P block, gallium is the first element in there, so 4p1. So you can memorize Aufbau's principle, or you could just read the periodic table, and it does take practice, so keep practicing. Let's do one more. Let's do magnesium. Magnesium has 12 electrons, so 12 protons, so 12 electrons for a neutral atom. We would start at the top, row 1, 1s2, 2s2, straight across, still on the second row, 2p, count all the way across, 6. Third row, 1, 2, so 3s2. Keep going straight across, we're on, that puts us at magnesium, so we're done. We're going to stop there. And there's the electron configuration. Try the problems that are on the Google form. Try using the periodic table to see if you can read it across.